Today we are going to discuss electric potential due to a dipole. A dipole is two equal and opposite charges minus q and plus q separated by a small vector distance to L. Let O be the center, then AO must be equal to L and BO also must be equal to L. P be the point which is at a distance AP from minus q charge and BP from plus q charge. P is the point which is at a distance R from the center at an angle theta. Now I am just extrapolating this particular line and dropping perpendicular from B to this line, that meets at D, and dropping perpendicular from A to this line, and that meets at C. Now what is this distance? In order to find out that distance, let us take this right angle triangle. From this right angle triangle ODB, you can see cos of theta is equal to OD divided by L. Therefore OD is equal to L cos theta. Similarly, from right angle triangle OCA, cos of theta is equal to OC divided by L. Therefore OC is equal to L cos theta. So we'll be using these particular distances OD and OC in this derivation. So the point P, there are two potentials. The negative charge creates a potential over there and a positive charge also creates a potential over there. The potential at P due to positive charge is V plus, and that is given by 1 by 4 pi epsilon 0 charge divided by distance. PB is the distance of the point P from charge Q. The negative charge creates a potential that is V minus 1 by 4 pi epsilon 0 minus Q divided by PA, where PA is the distance of charge point P from minus Q charge. So two potentials acting simultaneously at this point. Therefore the net potential according to superposition principle V is equal to V plus plus V minus. So that is given by, let us substitute these two equations over here. 1 by 4 pi epsilon 0 Q divided by PB minus of 1 by 4 pi epsilon 0 Q divided by PA. So certain things are common that can be taken out. Q by 4 pi epsilon 0 can be taken out into 1 by PB minus 1 by PA. Put as equation number 1. Now very carefully listen. The distance between the charges is very small. 2L is very small. Therefore, actually this point B is very close to O and point A also very close to O. Since L is very small and B is very close to O, the distance PB is equal to distance PD. PB is equivalent to PD. This is happening only because 2L is very small. And what is PD? The distance PD is nothing but PO minus OD. PO minus OD. Similarly, the distance PA is equivalent to PC, and that can be written as PO plus OC. PO plus OC. Now OD we already obtained, that is L cos theta. OC also we already obtained, that is L cos theta. Therefore, this equation PB can be written as PO minus L cos theta. Now, what is PO? PO is nothing but R. Therefore, PB is equal to R minus L cos theta according to this equation. And PA is equal to R plus L cos theta according to this equation. So, we got the equation for PB, that is R minus L cos theta, and PA, that is R plus L cos theta. Now let us substitute this particular equation in equation number 1. We will be getting V is equal to Q by 4 pi epsilon 0 into 1 divided by R minus L cos theta minus 1 divided by R plus L cos theta. Then just cross multiplying and solving, we will be getting V is equal to Q by 4 pi epsilon 0 into 2L cos theta divided by R square. 2L cos theta divided by R square, and we already studied that Q into 2L is nothing but dipole moment. Magnitude only we are using because dipole, the potential is a scalar quantity. So just to substitute the magnitude of Q into 2L as P, we will be getting V is equal to 1 by 4 pi epsilon 0 into P cos theta by R square. So this equation gives electric potential due to a dipole at any point, at an angle theta, at a distance r from the center, at any point. This equation can be considered as a general formula for the electric potential, and we are going to study the different cases. The first case number 1, if the point lies on the axial line of the dipole, obviously theta is equal to 0, therefore V is equal to 1 by 4 pi epsilon 0 P into cos of 0 divided by R square. We already studied cos of 0 is equal to 1, therefore V is equal to 1 by 4 pi epsilon 0 P by R square. Now case 2, at any point on the equatorial plane of the dipole. Equatorial plane means a perpendicular plane passes through the center of the dipole. If I am taking the point on the equatorial plane, then there will be no theta. So there will be a theta is equal to 90 degree. Cos of 90 is equal to 0. Therefore, V is equal to 1 by 4 pi epsilon 0 P into cos of 90 divided by R square. Since cos of 90 is equal to 0, V is equal to 0. So that means at any point on the equatorial plane of the dipole, electric potential is 0. But we already studied that electric field is there at any point on the equatorial plane of the dipole. Is it possible to have 0 potential and non-zero electric field? The answer is yes. We just proved that at any point on the equatorial plane of the dipole potential is 0, but the electric field is there. What is the value of electric field at any point on the equatorial plane of the dipole? Electric field intensity can be written as 1 by 4 pi epsilon 0 P divided by R cube. So this is a case of non-zero electric field and 0 potential. So answer for that question is yes, it is possible to have non-zero electric field and 0 potential. Now we are going to study equipotential surfaces. What is meant by equipotential surface? The name itself indicates if the electric potential has the same value everywhere on a surface, and that particular surface is called an equipotential surface. What are the different examples for equipotential surface? The first one is concentric spheres around a point charge. So this is a point charge. I am drawing concentric spheres around a point charge. So a particular sphere I am taking, and I am taking 2 points on that particular sphere, A and B. Since these are the point on the same sphere, the radius remains same. Now what is the potential at A? Potential at A is VA. And what is the potential at B? Potential at B is VB. And the potential at any point on this sphere is given by 1 by 4 pi epsilon 0 Q divided by R. As far as radius remains same, every point on this sphere, the electric potential remains same. So concentric spheres around a point charge is an example for equipotential surface. You please just note the direction of electric field. Direction of electric field is radially outwards if it is a positive charge, and direction of electric field is radially inwards if it is a negative charge. The electric field and surface has an angle 90 degree. So electric field passes perpendicular to the surface, that we will prove later. Now second one is surface of a charged conductor. Let us consider a spherical conductor which is charged. We already studied the charge will reside on the surface only, and this surface also is a example for equipotential surface. We will be proving that the potential due to the charged conductor at any point on the surface, V is equal to 1 by 4 pi epsilon 0 Q by R. Q is the total charge given on the surface and R is the radius of the surface. Therefore, since Q and R remain same, everywhere on the surface electric potential remains same. So the surface of a charged conductor is an example for equipotential surface. And the next one I have written, the vertical plane passes through the center of the dipole. So this is a dipole minus Q charge plus Q charge. separated by a distance to L. This is the center of the dipole. If I am considering a equatorial plane or vertical plane, we already proved that electric potential remains zero over there. At any point on this vertical plane, electric potential remains same, that is zero. Since electric potential remains same, even if it is zero, it is not changing. The potential remains same. Therefore, this also can be considered as an equipotential surface. So equipotential surface is nothing but a surface in an electric field where electric potential has the same value everywhere. Now we are going to discuss properties of equipotential surfaces. The first property is, you can read like this: no work is done to move a charge over an equipotential surface. No work is needed to move a charge over an equipotential surface. Why it is like that? We know that the work done per charge is equal to potential difference. VA minus VB is equal to W by Q. A is the point where potential is VA, B is another point where potential is VB. If the surface is equipotential, then the potential remains same. VA is equal to VB. Then the work done W is equal to Q into VA minus VB must be zero. So that means no work is needed to move a charge over an equipotential surface. Now the second property is that we already discussed: electric field intensity is always perpendicular to equipotential surface. Electric field intensity will be always perpendicular to equipotential surface, or electric field lines passes perpendicular to equipotential surface. That we are going to prove. So once again we are taking the equation for electric potential in terms of electric field. We studied in the first chapter, first topic itself, VA minus VB is equal to minus integral B to A E dot dl. Now VA minus VB can be written as minus integral B to A E dl cos of theta. Now let us consider these 2 points A and B is lying on an equipotential surface, are lying on an equipotential surface. Therefore potential remains same. VA is equal to VB. When VA is equal to VB, what is VA minus VB? VA minus VB becomes 0. So that means 0 is equal to minus integral B to A E dl cos of theta. Now very carefully listen, left hand side is 0, the right hand side also must be 0. But E not equal to 0, it is non-zero electric field. dl, the surface, not equal to 0. The elemental length we are drawing on the surface has a value, therefore it is not equal to 0. Left hand side must be 0, right hand side also must be 0. Therefore any of these three quantity must be 0. E not equal to 0, dl not equal to 0. The only possibility is cos of theta is equal to 0. So that means theta is equal to cos inverse 0, that's equal to 90 degree. What's the meaning of that? Theta is the angle between E and dl. If it is an equipotential surface, angle between E and dl is 90 degree. That is what we proved. So that means if we have an equipotential surface, electric field lines always perpendicular, or electric field intensity is always perpendicular. Direction of electric field intensity is always perpendicular to equipotential surface. It will be crossing like this only by keeping 90 degree with the line drawn on the surface. So dl and E must have an angle 90 degree with each other. So that is one of the important property of equipotential surface. The next property you can read like this: equipotential surfaces cannot intersect each other. What happens if they intersect? If they do so, that means at the point of intersection, the same point will have two potentials. That is impossible. The same point must have only one potential. If they intersect, if two equipotential surfaces intersect, at the point of intersection, the same point will have two potentials, and that is impossible. Therefore two equipotential surfaces will never intersect each other. Another property is the spacing between equipotential surfaces indicates strength of electric field. So if I am drawing equipotential surfaces which is always perpendicular to the electric field, this is electric field direction, and equipotential surfaces are crossing perpendicular to the electric field, and you can see if it is a strong field, the equipotential surfaces are spaced together, means the spacing will be less. If it is a weak field, you can see they are spaced apart. So the spacing between equipotential surfaces indicate strength of electric field. These are the main important properties of equipotential surface. Once again, what is equipotential surface? Equipotential surface is a surface in an electric field where electric potential has the same value everywhere.